Okay, when you hear about cavitation, the cavitation occurs due to the action of a tension wave. Okay, so tension wave. Willis asked questions. I'd like to share that together. I thought it's really worth it to. That's the reason I really take time to show you the phenomena, because once you hear, it looks like it's okay. It's okay, I can feel it. Then after for a while, then when I explain something else, then it pops up saying, geez, why, So that's why I usually mention two or three times the same things. So here, I'm also tired today. I think you are tired too. So, okay, this is a charge. Okay, this is a charge. And this is like a target. And when you consider the tension wave, this is what? Image charge. Okay. Then the first wave which reflect from the surface, the way you find is you draw the line. It's a mirror image is what I'm doing it. So I wrote a symbol like this saying this is a positive, it's a compressive wave. So at the time of explosion, the shock wave will propagate. It's going to go here and hit it here. Then it will reflect here. Okay? And here, the wave front is compressing the water, right? And behind, as a shock wave compress the water consists of really infinite number of fluid particles. It's compressing. So this is incident shock wave is compressing the water. Behind this wave, fluid particle is also there. So the wave will wake up the fluid particle. Then it takes motions. Okay? So then I said, that's the image charge, like an attracting source. So the easiest way to think to make the physics right is as it reflected, the fluid particle is moving toward what? Toward image charge, right? So it's all going up there, right? It's going up there. As the fluid particle along this line is going up there, wave front is coming toward the target, right? So this fluid particle is moving toward the image charge, means fluid particle is really breaking off each other. They were so friendly at the beginning. It's homogeneous water. It's all same kind of water. Then now it's split. Split means try to breaking off. Okay? So then wave front is coming down. So fluid particle is moving that direction. So I call the, let's say, U prime. U prime is correct. Then this guy is moving, C naught is moving in that direction. So that's called what wave? Tension wave. So tension wave. This tension wave, this pressure behind the incident wave is really positive, it's compressing. This guy, this portion is split, and the wave front is negative. Another way of thinking is this is time t, and this is pressure P. So until this guy, well, this is incident wave. Until this guy hit the target, that's called, this is R. It's very quiet. Shock wave is moving and hit the target. Then how long it takes to get to the target? How long? I call the C1 T1. T1 is equal to R over C, not time. It takes a time, bang! And reference time here is 0. This is a wave, start right here. Bang! Then it hit it. Then it has, of course, a tail portion. So the wave here is hit it. Then as time goes by, it's going to reduce. So strictly speaking, if you say this is absolute velocity, it's going to be right here is what's this? P atmospheric pressure plus P hydrostatic pressure up to this depth, right? Everything all goes like that. Then this is T. Then bang, it shoot up. It hits up to the max. Then down, converge to this point right there. For incident shock wave is concerned. But for this one, for this wave, reflected from the free surface back in here, this distance is same as that distance. So that means this plus that distance is from here to here. So I call this is what? R1, whatever, right? So R1, so how long does it gonna take to get to here? First to here, down to here is the same distance for that. So sometime later here, this is let's say the time it takes is, let's say, T2. T2 is equal to what? R1 time T after the T time, right? Because this plus that is longer than that. So we'll take a little bit longer, right? So now this guy is a tension wave. Tension wave is down here, then move to converge to 0. Negative wave, negative pressure. So now what you can do is, what happened? What would be the total pressure here? Total pressure after the rarefaction wave or tension wave hit it. If after this tension wave hit it, if the resultant pressure, if that's the 0 or below 0, then that point is cavitated. If it's a plus, it's not cavitated. So if I put the resultant, this plus that, at the beginning comes like this, then shoot up, then comes down exponential decay. We're going to look at today. Then you have that much below. So this plus this, maybe this could come down that much. Then now just algebraically adding up, then it will, you add this guy, so it will go up here, and some with another pulse, or from the bottom reflection it could come up, stay there. Don't forget, this is very basic, very important here. So now, look at this. We have another color, no other color. It's a little bit, I do a little bit small, but you should be able to see. Then, water cannot sustain the tension. So water can usually sustain the vapor pressure, which is something like a 0.3 or 0.4 psi. And water become vaporizing. Vapor pressure. Vapor pressure. You will see, you see all in my note. But when water really breaks off its molecular level, it's just total knockdown is zero. Or some people still insisting, chemists insisting, water can sustain -3 or 4 psi. It's called the breaking pressure. This is called the breaking. Some people say, oh, water still can resist. It can handle -3 or 4 psi. But usually in computation, you set the 0. Water cannot sustain the tension. When P is equal to or less than 0, then you declare the cavitation occurs in the water. Okay? It's a bubbly water. So in other words here, it's not going to go down below 0, even if mathematically when you add up, it's going to go down to below 0. You stop right at P is equal to 0. Cuts off. The reason is water cannot sustain the tension. So it just comes down 0, then goes up. For any computation, please do like this. There is no reason to fight dealing with the 3 or 4 psi. Not worth it at all. So if I just remove it, then result wanna be like this. This is called, it has a name. This is called surface cutoff. When you put the pressure gauge in the water, conduct explosion testing, then if you see the plot comes down exponentially, bang, cuts off, then drift away. Okay? This is surface cutoff. Due to tension wave, this is only portion which has a tension wave. It's keep coming until you really get the good grip on it, then I stop. I said that this portion you can neglect it because Nowadays you don't need to go through approximation, but okay, more on shock wave. Acoustic approximation is adequate, of course. Change in density, water density is small. That's what we are working. That's the range we are working on it. Wave propagating from different source proceed as if other does not exist. In other words, you can just superpose together as a linear wave. You don't have to worry about nonlinear wave for the explosion problem. Okay? So this is what I did here. And terminology, the reflection and the transmission wave, what is it? You tell me, your turn to talk. So start from the lead maybe. Reflection wave, transmission wave. Is it same? Reflection, transmission wave, like water. Whenever the shock wave hit some boundary, it reflected or can transmit into it, goes into it, penetrates, sometimes called refraction. Refraction is same as transmission. And diffraction is a little bit different. In case that obstacle or boundary is of limited extent. In other words, the diffraction, you turn off the flashlight. You turn off the light, then turn on the flashlight, and you turn on the flashlight. Of course, outside is dark. Then you go around, look at the behind it, then wave diffract in the back. You can still see the back. That's a diffraction effect. Not much in naval ship shock problem, but it's kind of the part of the arts. Scattered wave is somewhat important. You will see the action of this scattered wave. Scattered wave, or in this case is a pressure. Wave generated due to the motion of the boundary. What does it mean here? Is this is a flexible. Flexible. Then shock wave comes, hit it. Then if this is hit it has elastic property, it moves back. But water is in contact. Hit it, then water is there. It keep coming back up to the limit. Then the plate will push this back. Okay, this is a scattered wave. Scattered wave is the wave induced by the moving plate. Moving boundary. Makes sense, right? Hit it, this guy, flexible plate will push it back. So this push it back is a wave action as you look at this water. Well, you will see. You will see some section heavily when you get to the generalized Taylor plate theory. Wave generated due to the motion of the boundary or plate, whatever. Compression wave, incident shock wave, compression wave, flow behind the shock wave front. Rarefaction wave, tension wave, like a surface reflection wave is rarefaction wave. R-A-R-E-F-A-C-T-I-O-N. I thought it's F-E-C-T-I-O-N. But what I wrote is pretty correct. Rarefaction wave, okay? So it's all different types of the wave. That's about all you will hear that in the ship shock situation. So this is kind of a worth to make a note. So so this is a pretty interesting one. This is taken from the one of the Naval Research Lab. It's not Naval, Naval Surface Warfare Center report. It's all. This is an unclassified page. This is a form, and this is a plate, and it has an opening right there. Think about just the infinite plate, and some portion is a foam. What does it mean, foam? Like a styrofoam. You have a styrofoam cup, right? Styrofoam cup. This foam is like air. Shock wave cannot penetrate. Shock wave cannot penetrate. Here is a ship. Did I mention to you? Styrofoam, surrounding styrofoam. Shock wave come hit it, cannot penetrate. So that's the nature, like the air. Okay? So when the shock wave, this is a charge, explosive is here. So this portion is a part of the incident shock wave. If there is nothing else here, this is going to be all coming down like this. This is a portion of incident shock wave which went through the hole. Make sense? Makes sense, right? And this is a steel. This is steel. When wave hit it, it reflects from the steel surface, but it transmits right through also. And shock wave love it. What's the acoustic velocity in the water? I asked more than 10 times. What is it? 1500 psi. What about the acoustic velocity in this steel plate, Hassan?
5 times higher than air.
About right.
5,000.
About 7,000 or 8,000 meters per second. Well, 1500 times 5. It's about 75 or 8,000 meters per second. So when you tap the plate, it generates a wave in the solid, in the plate. The wave speed goes something like 8,000 meters per second. Remember. So here, listen carefully. Now here, this is a part of the incident wave drawn here. Here, this portion. Anyway, somehow. It's a wave, part of the incident wave. And when the wave hit the foam, it reflected. It can't penetrate. Wave cannot penetrate in the air. Same property as air. Okay? And let's look at the big wave here. So now as you look at this guy is opening here, so shock wave will penetrate through this opening, and here is diffracted. I said just to put the flashlight on, then as you go behind it, it's still light there. It's due to the diffraction. Okay, so due to the diffraction, behind is a little bit light. The light, you can see it. Okay, and also, okay, this is done. This is done. And also, when you look at this portion is also diffracted. The light, as it hit it here, and it's going to reflect back, and the wave never discontinue. Wave is always continuous wave. From this point, it's going to continue to here, and also the wave reflect right here as the incident shock wave hit it. So it diffract out like this. So it continues here, then diffracted here, this way. And this wave, this portion, is reflection from the plate, and this portion is transmitted through the plate, transmitted. Is very clear. And I just put this line here. As you look at the wave is all coming here. This is kind of straight into the plate, and it's going to reflect back out here. And this angle is alpha. So here in the instantaneous time, this is kind of the wave front with the alpha angle. Alpha grows as the wave is moving. Of course, this line is moving like this, so alpha angle is increasing. Think about the rigid surface reflection problem or free surface reflection problem. So for spherical wave, this is increasing. Then what happened? It's interesting. This is really application is not much about the head wave, but it's some phenomena I want you to know. And as alpha angle, well, first of all, the acoustic velocity along this boundary is c divided by sine alpha. The wave, this is rigid. The wave front here, as this guy is hit, and this angle is alpha, and the acoustic speed, as you look at along the boundary, the speed is c naught divided by sine alpha. Snell's law, think of three terms, right? C naught over sine alpha. This guy. So this, as the shock wave is moving, this alpha is increasing, but as alpha is increasing, C naught over sine alpha decreases, right? Makes sense, right? Because this guy is increasing to 1 limit value. So this guy is decreasing. As this guy, look at Chong'an, this speed along the boundary in the water is decreasing. And as this guy is decreasing, then what happened? As this guy is decreasing, in the still plate, the speed is so high, which is something like 8,000 meters per second, then this is getting behind it as alpha increases. Then still plate is, oh, you are slowed down. I'm going to pass you. It just passes zoom. Then it generates so-called head wave, or it's called the false wave, kacha wave, false wave. So that comes ahead of the rear wave, and it just comes right out, because this point is keep pulling down, and this wave is coming straight out, hit whatever the target is. Then this does not carry much energy at all. This wave doesn't have a strength. It's called a false. Okay? You got it? Say yes, yes, got it. And same thing happening in the other side. So this wave comes straight out. It's called a head wave or false wave. It's worth to note. Remember, foam, styrofoam, shock cannot penetrate. So that's the stopper. That's the reason, Chorong, I mentioned to you as a part of the thesis work for the shock mitigation, not only just the plastic, maybe similar material, so on, may do to protect the ship. You investigate. So that's the topics. Okay, this is for the really charges here. This is image charge. This is a wall. Okay, then explosion occurs right there. Then you got the similar false wave it can generate. And if this is really steel, it can really pull down. So it generates the head wave. Another case I'm just showing you. Over here, this is it's all similar, talking about the head wave. So this is a charge. This is a charge, and shock wave. If you draw the radius, is all same radius. So this is incident shock wave front, and this is an image charge from right there. Okay. And if you draw the circle, this is the same radius. This is the image charge. From the bottom reflection is from here. To get that, the point, you have to draw the line. It goes out like that. Anyway, and this bottom can be rigid or C0 over C1 could be different ratio, depend on the material, right? It could, in this case, just as example set as a half. So then if this guy eventually could pull out here, then it generates the false wave or head wave. Hit it. If your target is right here, this can hit first before the incident shock wave. In my class in the state, it's almost all the naval officer. And I asked them whether they have experienced a head wave. Couple of submariner, they mentioned for some testing situations and some situation, explosion, when explosion occurs, they have experience on the head wave. A little bit feels something coming. Then in next moment, bang, onto it. Head wave falls away. It has not much energy into it. Okay, so some example. This is a diffraction. So when wave hit it behind the high frequency wave, low frequency wave, you take a look at. But this is worth to note. This is the equation for acoustic velocity in the water. This equation is good for acoustic velocity in the water, for the ship shock situation, not good for underwater acoustics. Why? Underwater acoustics, wave can go down 30,000-40,000 meters below. Okay? Then pressure is a big parameter to affect the acoustic velocity. But in the range that the surface ship and submarine operate, this is good enough. I mentioned to you already. And pressure is not the parameter, important parameter. So here C, this is a unit dependent. C is a feet per second. Okay? And 4577 plus 11.5, this temperature is in C, Celsius scale. So if temperature is something like 25 degree, 25 times what? 25 times 11, how much? What, 28? 280? 280, you add on to it, 280, so which comes about 4,800 or something, 4,900, right? Plus S is salinity, salt content as a part per million. But range is very small, 34 to 37. Low value is 34, high value is 37. So almost a fixed number. So over here, 4.6 times 37, what's the value? Quick. 4.6 times 5 times 35. 150 average, okay? So 4577, 150. Okay? Add about, let's say, 300. How much? About 5,000, isn't it? Right? It's about 5,000 for the design. So I keep saying, use just the 5,000 feet per second, or 1,500 per meter per second, things like that. That's good enough. In the morning I said, for design-oriented person, always accept, no problem. Analytical person has to count to 3.25976, hopeless as an engineer. Right? It's okay. So this is very good equation. You can compute if temperature and salinity is important. At summertime, Indian Ocean and Atlantic Ocean or Pacific Ocean temperatures is very different. Indian Ocean can go up to about 89 degree Fahrenheit. 89 degree Fahrenheit converting to C. Can you do that? What's the temperature in C? 89 degree Fahrenheit. Can you convert to C? Convert it down to C. 32 degree. 32 degree over here. You can do that. You know the equation? You forgot? I think it's 5/9 F minus 32, something like that. This is a worth to remember. Okay, and this concludes finally 2.4. Took a little bit long time. It's worth it to discuss quite a bit. I use this is mine too. Just a minute. Oh, this is different one. You have this note. I didn't send out the I didn't send out the derivation of bulk cavitation equation. We are not there yet, so we're gonna do this. I got it in my office, so I'll send you tonight. Too tired, so maybe Monday I'll send you that. Because after tonight, I'll be out. So, okay, underwater explosion phenomena 2. So, would you read this kind of paragraph? I always put that in. And here I put the yellow, 5,000 feet per second. What is it? The value of the speed of sound is usually taken as 5,000. Pretty good. Now we're going to talk about I want you to read all this, okay? I want you to talk in this chapter all the empirical equations that you need for shock calculations by hand, okay? For complex problem, of course, you can do by hand. Then you have to use a tool, which is nothing but the software. MATLAB is a tool. So the code we are using is LS-DYNA. That's a code. That's a tool. So nowadays, one of the success lies how to use a tool well. Okay? You're so young, right? It's not in my age, but for your age, you should use a MATLAB kind of pretty well. How many knows MATLAB? You know MATLAB? Youngwon? Everybody know? How about Lee? At least, right? All the days we never learned the MATLAB kind. We just use a Fortran code. That was the only one you mess around with. It's not long time ago. It's not. It's not long time ago. Still, MATLAB pop up. When MATLAB really came out, really started using in college, maybe 80s maybe. It's not long time ago. And here, I'm going to give you all the necessary empirical relation. What's empirical? What's that means? Empirical.
Based on experiment.
By the experiment. All this is done by the experiment. Lots of real phenomena you can create by simulation. You cannot create by analysis. All the empirical, you put the charge, all different kind of the charge. You put all different types of the charge. You put the charge in different depth and conduct the testing. Then develop the equations. That's what happened. And Lawrence Livermore Research Lab. It's LLM? It should be LLM. Livermore Lawrence Research Lab, whatever, Research Lab. There is a thick report on explosive. I forgot the authors, and if you go in internet, you should be able to find. I had two volume, two separate volume. One box lost on the way out here, gone. So never found it. So, but you can purchase it, $10 or $20, and all kind of the statistical data. It's unlimited. This is unclassified, unlimited report. And this is all coming from there. Okay. And first equation, very important. Sometimes I use a capital P, or sometimes a small p. Same. Okay. So it's the same. It's equal to P max times e to the minus t over theta. Think this way first. P max, maximum pressure, and theta is called decay constant. Words to remember. Decay constant. T is a time. E is exponent, right? And P max, maximum pressure, this guy, is a function of charge weight. I always use W, charge weight, and the charge type. HBX1, typical charge the US Navy is using, is much stronger than TNT, and it affects P max. What I'm doing here is, this is explosive, and this is a gauge or target, same thing, gauge, a target. Then bang, then shock wave will hit it. It was very quiet. For gauge, don't feel anything. Bang! Until shock wave hit it, everything was good, calm. Then at the time of the bang, so I'm going to set that this guy is reference time, called reference time 0. That's the time the target recognizes it. Bang! Feel it. Oh, something came up there. Okay? So start counting the time. So if I draw T and the pressure P, if something not clear, let me know. I'm talking the gauge dynamic pressure. What does it mean, dynamic pressure? I remove hydrostatic pressure. Static part, you can always add on to it, just I removed it. Interest is a dynamic pressure. Now my reference time is 0, right there. Then start counting. Then shock wave will come, pass through, right? So at the beginning it's a bang coming up. This is P max. Exponential decay just like that. It's okay? 괜찮아요? It's done like this. From P max down to 0, this is exponential decay, is exactly this equation. And this decay rate, whether this comes like this, or this comes like that, or this comes like below, that's controlled by the theta, which is called a decay constant, okay? Decay constant, of course, this is a millisecond. This is, and T is millisecond. P max gonna be like a PSI usually. And this guy gonna be PSI. Usually unit dependent, but for this equation it's not unit dependent, but that's what I mean. Because if it's millisecond, you use a millisecond, the unit cancels, right? Then this is only P max, this is gonna be P. If it's a megapascal, then this is megapascal. This, if you wanna use second over second, got it? Unit, you have to be careful. So this is decay constant. Decay constants depend on this, whether it's like this or whether like this. Got it? That theta is a function of W and charge type also. And also the distance r from the charge. Distance r from the charge type and r. Let's see. So this guy comes like that. From 0 to time to about the 0, this takes about 3 or 4 milliseconds. That's it. Okay? What's the 1 millisecond? 1 over 1,000 seconds. 3 or 4 over 1,000 seconds. Everything done. Shock wave is just gone, done. Okay? So fast, that's what I'm saying here. And that's the graph I can draw it related to this. Okay, then P max is up there. I'm going to just put the inside here, P max. But what happens if you want to set the reference time? I want to set the reference time equal to 0 as time to explode. When detonation occurs, I'm going to start to count t is equal to 0 rather than t is equal to 0 here. You follow me? Right? You follow me, right? So I'm going to count this time, reference time, right here. When it explodes, I'm going to start counting it. Then from here to here, it takes a time, right? So it takes a time, how long? If this is r, it takes a time t1, which is r over c0, right? It takes a little bit time, so how can I modify this guy? How can I modify this? I'm going to move this point here, set this guy as 0 rather than here. Move how much? Move how much? From 0 to t1. Make sense? Then This is include only dynamic pressure. So this is P is dynamic pressure, dyna pressure. Okay, dynamic pressure right here. So this is so until the shock hit to that point, it takes time T1. So you have to move that only. It's the same thing, right? No difference. I wrote it down over there. That's what that exactly means here. Got it? Got it. So, however, I said, is it really exponential decay when the explosion occurs for TNT or HBX1 or C4 whatsoever? Is it really follow exactly exponential decay all the way down to the end? Then I can use exponent E. Okay, as a designer who opened their heart wide open would say yes. But whoever has analysis in mind, then say no. It's not going to be follow exact exponential forms. But up to the one decay constant, here, up to one decay, which means one decay. So I'm going to say up to the one decay, theta is the T is a theta. This is going to be equal to what? This is what? -1, right? So which means if I just put here, this is P max, 1 over is a minus. So if you do that, it's going to be 1 over E. Can I do that, right? What's the E value? 2.8 something, right? So can I say with the designer P max, hey, let's say 1 over 3, how does that sound, Hassan? Accept it? Say yes, accept it. Well, he's good. Good to me. It's acceptable. About 1/3. About 1/3 P max up to here, about the 1/3. Is it 1/3? About here, about the 1/3. P max about the 1/3 up to here is good. What that means is based on the experiment as review the result, about up to 1/3 is perfectly exponential. You can use it. You can claim it. Okay, but after 1/3, no guarantee whether it's going to be 1/3 or going to be like that or going to be like this. No guarantee. I'm a design-minded person. Then what I would say? Then what can I do? What I would say? Oh, that's okay. I'm going to just use exponential all the way. This is all I have. All the way exponential. I'm going to use it. Any problem? No problem. So that's what I'm using it. All life long I'm using it. I don't see anybody challenging for that. And that's good enough. Exponential decay. Whether T is only for 1 theta, which drive up to about the 1/3 P max, that's okay. That's what I'm saying here. P max and theta, there is a few parameter that has to be determined by the experiment. That's what the U.S. Navy has done. A lot of data came from the U.S. Navy. Then European people, they have same thing maybe they got it by agreement between U.S. Navy and Europe or Asian country. That two equation is very important. So here is a P. Again, we write this is equal to P max times. I'm gonna just write T over theta over here. T has to be greater equal to 0. It's all understandable. Then P max is equal to empirical relationships over there, parameter K1 and over R W 1/3 A1. Over here, W is charge weight equivalent to TNT, remember. Charge weight of the explosive unit dependent in pound, which is equivalent to TNT. For example, if this is explosive HBX1, if your charge is HBX1 100 pound, HBX1 100 pound sign, then when you can put the W, it's not gonna be 100. It has to multiply the multiplier equivalent to TNT, which is about 1.5. So then it has to be 150 pounds. Then you will put the 150. So if you put the note there, the weight of the explosive in pound equivalent to TNT. If this is a TNT, if this is not HBX1 TNT, then it's going to be 100 pounds. 100. You put the 100 as is. Clear? Clear. R is a standoff distance. This is a charge. This is a target or gauge. Straight distance is R. It's called the standoff distance. Always called standoff distance. Standoff distance in feet. Okay? So over here, R is in feet. W is in pound. P max is in pound. It's a unit dependent relationship. And the K1, A1 is charge type dependent parameter. I just listed a few very popular explosive in the back. Next page maybe, or couple page after. Very clear, right? K1, A1. K1, A1. Charge type dependent parameters. Very clear. And the theta is the decay constant. Theta, you have a K2. The next one is W to the 1/3. and W to the 1/3 over R to the A2. K2, A2, charge type dependent parameter for theta. W, R, clear. And theta is millisecond. Remember, R feet, W pound, theta millisecond. Okay? This is empirical relationship. They really experimented, then conduct a statistical analysis. To get the feel here, this is a 250 pound charge of HBX1 and is detonated at 20 feet from the target. So the R standoff distance is 20, R is 20, and HBX1 charge, I want you to find some mistakes here. Then find the incident peak shock wave pressure which will impinge on the target, which will hit the target. Same equation. This is for HBX1, K1, A1. If you look at the K1, A1, where to look at it? A few pages down here. Oh, it's not here? Wow. It's not here. It's the next section. It's not there still. Oh, it's here. Next section, 3.2-5. There is K1A1, K2A2, K3A3, all the parameter for typical one, HBX1, TNT, PTN, and this is nuke is nuclear. But this value is all valid, unclassified. PTN and the pentolite very close, the value is very close to each other. But this data is really PTN. So that's why I changed to PTN. This is a 3.2. So we are still in 3.3. I have to look at my another note to verify, because A1 K1, this is a charge type dependent parameter. Already charge type is accounted, so W I thought is equivalent. Charge weight equivalent to TNT, maybe in this case may not need to multiply like 1.5. I'll check before I see you Monday. You know what I'm saying? This is already taken account to look like here A1 and K1. So let me look at different the references to check out, okay? And I'll let you know. But if W, when you use a W, you are always dealing the equivalent, the charge weight of TNT. Everything converted back into TNT. Then you are dealing with the computation. But this is A1, K1 is here. So let me check and give you the correct answer Monday. Okay, anyway, so this equation, if you look at P max, get the feel, 6,000 psi. For this is only 250 pounds. Okay, Cheonan naval ship, you are talking about 300 kilogram, which is about 600 pound. 600 pound. So Pmax for 250 generate 6,000 psi, tremendous, at the distance of 20 feet. 20 feet divided by 3, about 6-7 meter, which is roughly the distance that explosion, torpedo explosion occurs in Cheonan naval ship. Tremendous. Theta is usually in the order of fraction of millisecond, okay? Otherwise, the exponential curve gonna be weird, okay? T1, what's a T1? Time the shock wave arrived to the target. It said 5,000, this is a feet per second, and 20 feet, so you have 4 milliseconds. So T minus T1 is moving the coordinates, so that's what you'll do here. And this, you know this equations, right? And that, okay. Next is worth to look at this. This is energy. This is energy per unit area per unit thickness. So when you deal with shock energy, you can say this is shock wave front. Is in next. This picture is in next page I draw. This is unit thickness, and area, shock area is this. So when you say energy, it's really energy per unit area per unit thickness. So which means energy per unit volume. Okay? And if you look at P, think of this P times P, what's the unit of the P? Pound per square inch times V times dt, velocity times time is distance. Pressure times distance. Work done over the unit area, but unit thickness is implemented, is already implicated. So work done is energy, right? So it's energy per unit volume. So that's what. So you can compute P. You can compute that for the plane wave. P is equal to rho c v or rho c u. So v is P over rho c. Then you can integrate P. You can use P. You can put this relationship right here. Or you can just put the P as a P max e to the minus T over theta, right? Then reference point is right at the target point. And this is kind of analytical forms, but empirical form you have here. This is really taken from the Naval Surface Warfare Center report. The reference is in the back of this chapter, I think. It's Pride, author is Pride. Price, P-R-I-C. This impulse. Impulse is area under. This impulse is area under the force curve. So here is force. If you have this time t. This is impulse, area under the force curve. For the shock wave, you're dealing with the pressure. You're dealing with the pressure, O raised divided by A. So you're dealing with impulse per unit area. Okay? The pound a second, this is impulse per unit area. Per unit area.